Okay, so let's start our lecture today, and let's see. So let me recall what I did last time. Yeah, this method is really good. It's like 20 degree Celsius, and it's like warm weather. So it's very good. Especially we were like, I think there are people like taking the graduation photo here. So yeah, so I think it's amazing that nice weather. So let me think. So, oh yeah. So I think last time, last time we analyzed the behavior of, so we showed that the lattices on the, so last time we showed that the lattices on the left half plane is symmetric to the lattices on the right half plane. And we also show that there are some patterns for the so we just focus on the right half plane, right? So so therefore we so focus on the right half plane. So points on the right half plane. And also remember that we are under the assumption this so I have my omega 1 and then this omega 2. So we are under the assumption that modulus of omega 1. So here omega 1 is in positive real, and omega 2 is in the I positive imaginary axis. And so this omega 1, modulus of omega 1 is bigger than modulus of omega 2. So modulus of omega 1 is equal to modulus of omega 2 times some constant, let's say k. Okay. And then let me see. So yeah. So we focus on the lattices on the right half plane. So we do the transformation. After transformation. So after the transformation phi, so which is being defined as from z to 1 over z squared, right? And then so I think what we get is that we'll get the limit with a gap, right? So it's like a quadrant. Yeah, I think there are only 2 points here. So yeah, and then we okay. And then wait, shoot, hold on. So the angle is double, right? So yes, okay. And then for the points on the denominator, so one is doubled. So it's getting closer and closer to this angle. So probably something like that. So what do we want to do now? So what we want to do is that we want to let me think. What do we want? So I think we fix the yeah. And so do I want to fix omega 1? Let's see. Omega 1 or omega. So it seems to me that if I fix omega 1, then there might be some vertical cancellation, right? So so there might be some vertical cancellation, like yeah, and then the horizontal part will be added. So basically, so let's see. So here and that W to be equal to n1 omega 1 plus n2 omega 2. So on this point n1 equal to 1, I would say that so points are cancelled out, I think. So the so basically, I can divide the whole line into the positive part and negative part, right? So let me see. So points. Points in the the invariant part. let's use those things 1 plus. Okay, so the positive part would cancel out with imaginary part of 1 minus and then what's left is just and then left with the real part, right? The real part so now let's see if we can sort out the real part of this guy. So so basically, this number, so let's use A and B. Okay. So let me. So let's see. So suppose. Yeah, because I don't want to write like I don't want to write the modular part, yeah. And then where B is in the positive real, and then and both A and B they are positive reals. So therefore so I get so if I have so here so what's the sum? So the positive part. So 1 plus part. Okay. So the sum of the 1 plus part is equal to the summation of I from 1 to infinity of so it should be 1 over A plus I shoot. And I should use another index, so maybe I use J. So A plus I, wait, I don't think it's gonna work. So maybe let's say N here, okay? And then I N, so maybe let's use M, because I think I in the past I used M for the X coordinate, and then I use M for the Y coordinate. So I M B, yes, squared. So which is equal to wait. sorry, I think this positive part corresponds to this part, and then this negative part after you do a doubling and then you do a reversed. Yeah, so it becomes here. So so then it is equal to so I only care about the real part. So summation to infinity of, so let me open the bracket here. So the square becomes a plus I and b, right? And then, so I get, a square plus 2 times I and b minus, so m squared b squared. So this is equal to 1 over a squared minus m squared b squared plus 2i and b. So now I multiply both sides by conjugate. So I get this one squared, right? And then the top is the same. And then for the denominator, so times minus that, I will get, so I will get a plus, right? 4 m squared b squared, yes. So for the real part, yeah, so clearly for the imaginary part, right? So when the m runs from positive part up to infinity, and then when the m run from negative part, because the denominator are exactly the same, right? So when m is positive and when m is negative, and then the numerator is exactly the opposite. So the imaginary part will be cancelled out for the imaginary part, and for the real part, right? So oh, I'm seeing my old friend again, I think. Okay. So yeah. So this one is like my I see. So let me do this. So this one I get m from 1 to infinity of. So let's focus on the real part. Okay. So the real part. So the real part is equal to I mean the real part, they should being added up, right? Yes, they should be added up. So So this is like just the a squared minus m squared b squared, and then a squared minus m squared b squared squared. Oh, sorry, plus 4m squared b squared. Yeah, so and together with the negative part, right? So actually, I think for the negative part, because here all the m they are in terms of m squared, right? So actually, because for each of the negative part, the sum will be actually for each m it will be added, right? So for each m it will be the same as the real part, so it will be 2 times this one. So yeah, so it seems that everything I think boils down into the really the angle that's in one quadrant, right? So so if the sum in one quadrant converge, then I think so then it's guaranteed that the total sum will converge. Yes. So let me think. So now we focus on the sum in one quadrant. So I know that. So initially I should have this one as n, right? So in this case, so in this case, if I have, let's say, if I want this to have, so then let me think in this way. So if I have the sum of the nth column, right, positive part, which is equal to, so summation m from 1 to infinity of, so here my coordinates are exactly NA, right? Yes, so NA. Yes, plus I and B. Same thing. So this is equal to, so let me just write here. So 1 over n squared a squared plus 2 I times n m AB, and then minus m squared b squared, right? Yes. And then so now let me simplify this again. So this is equal to let me just write it this way: n squared a squared minus m squared b squared, and then plus 2i and m AB. So now I multiply by the conjugates. So for the top part, I get n squared a squared minus m squared b squared. And then, so what I have is that I'm having so minus n m a b. And then, so this one is n squared a squared minus m squared b squared plus 2i n m a b times minus. Okay. And then, so this is equal to summation m from 1 to infinity of so top part. So now I'll keep the part 2i and m a b. And now for the bottom part, what I get is that n squared a squared minus m squared b squared squared. And then, so something will cancel out. And then it should be plus, right? So because I and plus 4. Yes, so n and a b, n squared m squared a squared b squared. Okay. For yes, okay. So now let's look at the real part. Okay. So let's look at the real part. Yeah, because yeah. So let me look at the real part. So it's equal to the real part of this guy. So of course the real part, like the real part. So which is equal to summation m from 1 to infinity of just n squared a squared minus m squared b squared. So over n squared a squared minus m squared b squared squared plus 4 n squared m squared a squared b squared. And then, so this is the n sum. So now, if we sum over the n here, so sum over the n. So what we get is that we will get summation n from 1 to infinity of summation m from 1 to infinity n squared a squared minus m squared b squared n squared a squared minus m squared b squared squared plus 4n squared m squared a squared b squared. Yeah, this is very familiar to me. Yeah. So the question is that does it converge? Yeah, let me check the time. Okay. Yes. So, yes. Just making sure it's recorded. So for the convergence, so yeah, so let's see. So when we have n squared, a squared, let's say somehow equal to m squared, b squared. So basically, we want to find the point where this is positive and where the point that is negative, right? So so I assume that you can actually take mn to be any real number. So if they are true, right? So just imagine that this n and m instead of integers, they are just the real x y value. So this is x value, this is the y value, and then so you get, let's say m over n is equal to a over b, right? So m is equal to so m is equal to n a times n times a over b, right? So so now, so let's let a over b equal to k. So in this case, m equal to nk. So let's draw the graph here. So m is like the y coordinate, right? So n is like the x coordinate. So let's draw the line. Y equal to x times k. Y equal to kx. So basically, this I'm kind of thinking that this a is bigger and like b is smaller. So this k is yeah. So this k is a little bit big here, and I think for points above this line, the y value is relatively bigger, right? Y is bigger than ks, so namely m is bigger than NAB, and then therefore m squared is bigger than yes. So so therefore m squared is bigger than n squared, a squared over b squared, and then you have m, yeah, so this is bigger than that. So yeah, so what I'm supposed to do next? Yeah, I want to look for some symmetry, right? So can I find some symmetry in this case? Or I think, let me think. N squared plus n squared a squared minus n squared b squared. So yeah, so yeah, so now the lattices, they are unit lengths, and for point that's above this line, the actual value is so points above y equal to kx, so the summand you get negative summand, right? So the numerator is n squared a squared minus n squared b squared is negative. And also for points below, right? So points below y equal to kx, then you have this one is positive. Yeah, I think I'm running into like a similar argument like before. So namely, wait, let me see. Is that the same argument that I did before? So if you fix A or B, if you fix K to be, let's say, some integer number, then you will have the line passing through like some points, right? And then when you do that, yeah, so we can express it as the lower sum and upper sum. Then you can find some cancellation. Yeah, so I think I'm also running the barrier argument here. So so if I run the barrier argument, wait. So if I run the barrier argument, okay, I think I need to get as much cancellation as I want in this case, right? So otherwise, if my estimate is so coarse, then I may not get the right result, I think. So how do I find my estimate? So namely, I think what I can do is that I can maybe separate the positive part from the negative part, maybe, and try to go from there. But can I really do this? So, I mean, so you always have the n as the positive part. Wait, I don't think I'm allowed to separate these two, right? Can I separate the n square a square and the m square b square and then do the I don't think I'm allowed to do that. Because I think rigorously speaking, so this is like I can do it definitely. I need finite sum, right? But can I do it in an infinite sum? So for an infinite sum, yeah, I don't think I can do that in an infinite sum because otherwise, you may get infinite sum of the n square and the infinite sum of the m square, and then that's gonna be infinity minus infinity somehow, maybe, or yeah. So let me think of yeah, and again, I think it's very hard to evaluate in this case because for the previous part, right, for the previous n square a square, it's hard. I think it's hard to find like a definite value for the positive part and also yeah. So I think maybe one way that so my goal So maybe it's to wait. So my goal is to get as much cancellation as possible. I feel like there might be some cancellation when we are summing over this line and also this line, right? Let me see. So maybe let me forget about the K for a while. So maybe let me just do like maybe ignore the diagonal for a while, and then let me just sum over the like sum over this row and this row to see what will happen. So so sum over row 1. So here n equal to 1 and m equal to 1 plus maybe. Let's use 1 plus to denote the so bigger than 1. Okay. Yeah. So integer sum of 1 and then all the y value being positive, being bigger than 1. So then we get so n equal to 1, right? So I get summation m from 1 to infinity of, so here I get, so this is a squared minus m squared b squared over same thing. So here I get a squared minus m squared b squared plus 4m squared a squared b squared. So now I sum over this bigger than 1. So the first row start with 2, and then so I get so basically I'm fixing m to be equal to 1, right? So I'm summing n from, sorry, this is m to be equal to 2. So n from 2 to infinity of a squared, sorry, it should be n squared a squared, right? So then this m equal to 1, so minus b squared over, so for the denominator, what I have is that I'm having n squared a squared. So now this becomes 1, so minus b squared. And then squared plus, so this is 4n squared, right? A squared b squared. So okay. So how am I going to cancel this one? So yeah, let me check the time. Oh, okay. So yeah, so sorry, I think I have to stop here. Sorry, yeah. So yeah, so let me continue next time. Yeah, let me come next time.